We have observed that matter can be found in either the solid, the liquid, or the gas state. In this video segment, we are beginning an introduction of gases, a physical state of matter, which we have described in earlier video clips as being characterized by having no definite volume. So we know that gases are compressible. We can take a balloon filled with air and squeeze it and change the volume, compress it. We know that gases have no definite shape. In other words, they're considered a fluid state of matter along with liquids. They will assume the shape of the container that they are in. And we observe that gas particles are far apart. It's hard to detect their presence because the empty space between them is so great compared to the actual size of the gas molecules or particles. So most of the gas is empty space, and that's what we observe. This information on gases is found in Chem 2A in Chapter 8, Section 8.1, and in Chem 22 in Chapter 11, Section 11.2. So let's dig deeper and come up with a more complete model of how matter behaves, or how we can just best describe it when it is in the gas state. And this model is known as the kinetic molecular theory of gases, a description of matter in the gas state. And because we will refer to the kinetic molecular theory so often, it is commonly abbreviated KMT for the first letter of each of the words. So what are the points of the kinetic molecular theory and its description of gases? Point number 1, a gas consists of small particles, either molecules or atoms. So for example, carbon dioxide, a gas, that is a molecule. Neon, another gas, a noble gas, that would consist of individual atoms. So a gas consists of small particles, molecules or atoms, that move randomly in straight lines with high speeds. And what observation can we make that supports this? We know that gases will diffuse to fill their container or to fill their space. So I can spray, for example, a small amount of perfume in one area of my room and go to another point, and that perfume, that gas, will diffuse and reach me, meaning that these particles of a gas must be moving. So gases consist of small particles that move randomly in straight lines with high speeds. Number 2, the attractive forces. In other words, the intermolecular forces of attraction that we have discussed or will discuss at some point in the class, abbreviated IFAs. These intermolecular forces of attraction between gas particles are so small, essentially they are not operating when matter is in the gas state, and we assume that these intermolecular forces of attraction are essentially zero. They're so small as to not be observable. So the observation that we can make to support this is that at a given temperature and pressure for which a gas is stable, for example, room temperature, room pressure, we know that oxygen is stable as a gas and will remain indefinitely in that state without converting to a liquid or a solid, right? So that must mean that there's no tendency for gas molecules or particles to collide and stick together. If they did stick together, then they would convert to either the liquid or the gas state, which are states of matter where the particles are in close contact with each other. So gases must not have any significant intermolecular forces of attraction operating between them, right? So when gas molecules collide, they don't have any tendency to stick together. They bounce apart in what we call perfectly elastic collisions, right? So that's a term that you may not have heard before. A perfectly elastic collision is a collision that occurs without any loss of energy between the colliding particles. One can speed up, another can slow down, but they don't lose energy, right? So we're postulating that gas molecules must have perfectly elastic collisions because there are no significant intermolecular forces of attraction. So therefore, they don't lose kinetic energy, they don't slow down, otherwise they would move slower and slower, start sticking together and form a liquid or a solid, but we don't see that happening with gas particles. So they just hit and bounce apart without losing energy and will remain indefinitely in the gas phase at a given temperature and pressure for which they are stable. Number 3, as we mentioned, most of the volume occupied by a gas is empty space. Therefore, the actual volume of the individual gas particles must be very small compared to the space between them, right? So lots of empty space separating gas particles, and the actual volume occupied by the individual gas particles is so small that we often just assume it's negligible compared to the container volume. What are observations that we make to support this? Well, we know that gases are very compressible. So because there is all of this empty space, you can take a gas and decrease its volume easily, right? Because there's so much empty space between the particles. We also know that gases have very low densities. So a lot of empty space for the actual mass that the gas molecules themselves have in that space. Lots of empty space lowers the density. Number 4, gas molecules will collide with each other and transfer energy with no loss of energy, right? So these perfectly elastic collisions, they're moving rapidly in straight lines. They will collide with each other and transfer energy. One may move faster, one may move slower as a result of the energy transfer, but no loss of energy. Gas molecules will also hit against the walls of their container, right? So a wall of the container, gas particle moving, it will hit against the wall of the container and then bounce off, again in a random direction, but moving in a straight line. Every time the gas particle collides against the container walls, it exerts a pressure, a force applied per unit area. So when gases collide against the walls of their container, they exert a pressure which is known as gas pressure, and we can measure that with various devices. The 5th and final point of the kinetic molecular theory is that the average kinetic energy, remember we talked about energy being either in the form of potential energy or kinetic energy, kinetic dealing with motion. The average kinetic energy of a gas is directly proportional to its Kelvin temperature. So the directly proportional means that if you increase the temperature of the gas, the average kinetic energy of the gas increases. Now, kinetic energy mathematically is 1/2 mass times velocity squared. So if you're increasing the average kinetic energy of the gas, you're not changing its mass, you must be changing its speed or velocity. So if the kinetic energy is going up, that means the gas molecules have to be moving faster. You're increasing their speed on average. They will collide with each other and with the container walls more often and more forcefully as a result of their increase in temperature. So one more time, the average kinetic energy of a gas is directly proportional to its Kelvin temperature. If you increase the temperature, you increase the average kinetic energy of the gas. That means its average velocity or speed is increasing. The gas molecules are moving faster. It's a 1, 2, 3 direct effect. Increase temperature, increase average kinetic energy, increase average speed or velocity of the gas molecules. Therefore, they will collide with each other and with the container walls not only more often, but because they're traveling faster, they will collide more forcefully as well.